Welcome to discussion 33. In today's discussion, we'll focus on section 6.2 on volumes, and in this video, we'll do examples involving volumes of revolution. So I want to look at problem number 7 from worksheet 15, which says consider the triangular region created by the points 0, 0, 1, 1, and 2, 1. And part A says if you rotated that region around the x-axis, what is the volume? B says, well, do the same thing, but now rotate it around the y-axis. And C says, well, if you rotate that region around the line x equals -1, then what's the volume? So first, I want to give you 9 total minutes to try A, B, and C here. Pause the video in 4, 3, 2, 1, pause it, and try these for about 9 minutes. All right, so hopefully you did that. Hopefully you paused it and tried these for about 9 minutes. Let's talk about them. So I want to begin part A by drawing a picture. So I'm going to draw some axes. Let me make this straighter. I'll draw some axes. Draw some axes. So we have a point at 0, 0. I'll put a tick mark here at 1, and 1 at 2, and then 1 at the y-axis. So there's a point at 1, 1, and at 2, 1. And it says consider a triangular region created by those points. So let's join them with straight lines to make a triangle. So we have this region, and it says we're going to rotate this around the x-axis now. So I indicate that by drawing this sort of curvy arrow line to indicate I'm going to rotate it about the x-axis. So I'm going to show what that looks like. And the way I begin is first I take this shape and I reflect it across that line. So I'm going to draw that. I'm going to draw that point 1, 1 reflected, 2, 1 reflected, and then I'm going to make this triangle shape just with dashed lines. So I draw some dashed lines, dashed lines, dashed lines. So that's what it would look like if we rotated it. Okay. Or sorry, that's what it would look like if we reflected it. Okay, so now if I were to look at some point like this on that region, as that gets rotated around the x-axis, it will come down, it'll reach some low point and then come back up. And if I look at some point directly above it at this upper region, that would come down. It would come down even further. This is further away from the x-axis, so it's going to have sort of like a bigger radius as it revolves around, get to a low point, and then it's going to come back down, or sorry, come back up. All right. So our region is going to be full of cross sections that have this shape. Let me draw one more. So let's draw one to the right of one. So if I were to take a point like this, bring it down as it rotates around the x-axis, and then it'll come back up. And then take a point directly above that. It'll come down further to reach this bottom, then it'll come back up, and we get this cross section. Okay, so that'll create this 3D shape where the cross sections look like, these are called washers. Okay, and what I'm going to do now is I'm going to give these washers a little bit of thickness. So the thickness will extend in this x direction, so a little bit of thickness. I'm going to call that length of that thickness dx to indicate it's in the x direction, and the dx means it's really, really small. Even this other washer, it'll have a little bit of thickness, Let's draw that in. Okay, so that length is dx. So recall that our formula for the volume is we take an integral, and so the thickness variable, in this case it's x, tells me the variable in my integral. It's going to be a dx integral. And recall the formula for volume will be the integral of the area of our cross sections. And that's going to be a function of x because this is a dx integral. Okay, and then for the limits of integration, the smallest x ever gets here is 0, and the biggest it ever gets is 2. So I need to find a formula for the area of these cross sections. So these shapes are what are called washers. So the area of a washer, that's a circle with a smaller circle inside that's missing, is pi big R squared for the big radius, and then minus pi little r squared for the small radius. Okay, so if I draw in the big radius and the small radius in the first cross section, whoops, okay, so here to here, this would be the little radius, and then from here to here, this would be the big radius. All right, so we get this integral from 0 to 2. I'm going to go ahead and take these pi's and factor them out of the whole thing, and I'll be left with big R squared minus little r squared dx. Okay, so now I need to be able to figure out, well, what is big R and what is little r? Well, I know that little r is going to depend on the equation of this line. By the way, if we figure this out, this would be, if we work this out, sorry, this would be y equals 1/2 x. And if we look at little r just depends on, well, what is the y coordinate at this point? What is that y value? Okay, I'm going to go ahead and substitute in what y is, which is 1/2 x, because I need to do that so that I get this thing in terms of x, because I have a dx integral. Okay, so the issue is that big R changes, like it sort of changes the curve that kind of dictates what big R is changes. And it changes at this point. To the left of that point, big R is determined by this line, whose equation is y equals x, if we work it out. And to the right of that, it's dictated by this line, which is y equals 1. So big R is going to be changing from, at a point like this, again, I need to take the y coordinate. The y coordinate will tell me how high up this is. And the y coordinate there, if I use this equation, y equals x, and I plug in for it, I'll get that big R is just x. Okay, so big R is going to change from that to being big R is, at a point like this, the value of big R from here to here would just be this y coordinate, which is 1. Okay, so because big R changes somewhere, we are going to split our integral into two pieces. So we will split this into two integrals, because on one integral I'll use one of the values of big R, and on the other one I'll use the other one. So we'll get pi, and then let's split up the integral into one integral. So because it splits here, I got to go from 0 to 1. And on that interval, my big R was equal to x. So we will get x squared. And then minus my little r. Well, little r was just 1/2 x. So we'll get 1/2 x being squared, dx. And then plus, now we'll have an integral. Let's try that squared better. The next integral goes from 1 to 2. And then on that interval, big R, we said was 1. We have 1 squared. And then minus little r is still 1/2 x squared. And we'll get dx. Close that bracket. Okay, so from here, we just got to do some algebra, take some antiderivatives. So I'm going to write dot, dot, dot. And I'll leave that computation for you and just say that this will end up being pi times this first integral ends up being 1/4. The second integral ends up being 5/12. And if we get a common denominator and simplify, this will end up being 2 pi over 3. All right, so we are ready for part B. In part B, it says to now rotate this region around the y-axis. So I'm going to begin with another picture. All right, so beginning with another picture. Okay, so our region looks something like, we have a point here, and then we have this triangle where this is 1, this is 2, and this is a y value of 1. So now we're going to rotate this around the y-axis. So I first am going to draw a mirror image of my shape reflected across the y-axis. So I'll get something like this, and this, and this. I reflected it. Okay, and now I'm going to start to draw the cross sections. So if I were to take a point like this, kind of closest to this axis of rotation, that's going to get looped around, it'll reach this far end, and then it'll come back. And if I take a point starting here, just further out in the x direction, here at this further edge, at this, whoops. So take a point like this, that would get looped around. It would reach this far end and then come right back. So my cross sections here again are also these washers. They're going to have some thickness. So let's draw the thickness. This time that thickness is in the y direction. So I'll call it dy because it's really, really small and it's in the y direction. So if we form our formula for volume, we'll get the integral. It's going to be a dy integral because my thickness is in the y direction. And our area function, then we need to write it in terms of y. So for the limits, the smallest y ever gets here is 0. And the biggest it ever gets is 1. Okay, so this will be equal to My formula for my cross-section is that formula for a washer. I'll pull the pi out, and I'll get big R squared minus little r squared. That's our area for a washer. 0 to 1 dy. And now I got to identify, well, what is little r? In my picture, that's this distance. And then what is big R? So big R would go to this point, and then to that axis of rotation. So looking at my picture, little r will depend on the x-coordinate of this point, because the x-coordinate here is 0. So I just need to know the x-coordinate of this point. I need to know that x value. And the equation of this line was y equals x. It was y equals x. I'm going to isolate the x and write it as x equals y. And I want to do that, and I want to say that this x is equal to y, because when I plug into my integral here, I need y as the variable, because it's a dy integral. All right. So at this point, we are going to have pi times the integral from 0 to 1. And then minus, I know little r is y. So we'll get y squared dy. I just got to find big R. So for big R is going to depend on the x-coordinate at this point. So I need the x-coordinate at that point, and that point is on the line. Let's see, its equation was y equals 1/2 x. Let's isolate the x. Let's multiply the 2 over, and that'll give us x equals 2y. So this x equals 2y, and that's going to be my big R. All right, so big R is 2y. And we have to square that to get r squared. Again, I'm going to leave this computation for you. And I'll just say that if we work this out, we'll end up with just pi as our answer. So for part C, it asks us to rotate the region around the line x equals -1. So that is a vertical line. Okay, so I'm going to draw a picture. So I'll draw y-axis, x-axis, I'll draw our shape. Which was something like this, where this is 1, this x-coordinate's 2, that's a y value of 1. Now we're going to rotate it about the line x equals -1. So we're rotating it about this line. So first, I'm going to draw the mirror image of my shape reflected across that line of rotation. Okay, so the mirror image of this point now is somewhere over here. And then if I draw my triangle, it would look something like, I'll draw the dashed lines. It would look something like this. Okay, and if I form my cross sections now, my cross sections look something like, if I take one of these nearer points to that axis of rotation, we'll get it coming around, going up to the end, and then coming back. And if I take a point further out like this, it goes all the way over, and then it comes back. Okay, and this cross section has a little bit of thickness. And that thickness is going to be in the y direction. Okay, so if I use our formula for volume, we'll get the integral area function in terms of y and dy, because the thickness is in the y direction. And the y values start at 0 here, and they go until 1. And I'll get the integral from 0 to 1. Again, my cross section is a washer, so we will get pi factored out, and then big R squared minus little r squared dy. And in the picture, little r will be from here to here, and big R will be from here, to this point. All right, so we need to figure out what big R and what little r are. All right, so let's start with big R. So big R is going to depend on the x-coordinate at this point and the x-coordinate at the center point. So maybe if I call this point x comma y, the center point would have the same y value, but the x-coordinate we know is -1. So big R is going to be, well, I basically need to subtract these two x values. That'll give me this length. So I do the bigger x value, which let's just call it x, this point's x-coordinate, and then minus the x-coordinate at that smaller point, which is -1. So this will give me x plus 1. But I don't want to plug that in, because then my variable will be x, and this is a dy integral. So I need to plug in what x equals. Remember, the equation of this line was x equals 2y with the x isolated. For this line, it was x equals y. Okay, and if I plug in the x value here, I get 2y plus 1. All right, so we're going to get pi times the integral from 0 to 1. I know big R is 2y plus 1. We'll get squared. And then minus, I got to figure out what little r is. I'll square it. I'll put dy. So now let's do little r. So little r is going to involve this x coordinate. Let me call this one x. And then the y coordinate, let me call it y. So little r is going to involve the x coordinate at this point, and then minus the x coordinate over here, which is -1. All right, so if we simplify this, we end up getting x plus 1, but now we're going to be plugging in the x coordinate on this line, which equals y. So we'll get y plus 1. All right, so that is what little r is. It's y plus 1. So we'll get y plus 1 being squared. So from here, we'll get pi integral. And if I square this first thing, I'll get 4y squared plus 4y plus 1. And then we get minus. And if I expand y plus 1 squared, we get y squared plus 2y plus 1 dy. Now I'm going to write dot, dot, dot. And I'm going to leave that antiderivative work to you. From here, it should be easy. And I'll tell you what we end up with, which is 2 pi. And that is our answer.